So next up we have Eric Mikida, another PhD student in the Parallel Programming Lab, and he's going to be talking about load balancing in PHOLD.
Okay, so as Michael mentioned, my name is Eric, and I'll be talking about a particular application of load balancing. Specifically, I'll be talking about how to balance load in parallel discrete event simulation where your load is now speculative. So to give a brief overview, a brief background on PHOLD for those that may not be as familiar with it, when you have a PHOLD simulation, your simulation is made up of many logical processes, or LPs, as well as a large number of events. These events are all tagged with some virtual time and directed at a particular LP. And to do the simulation, the LPs just process the events in timestamp order. So in a sequential system, this is pretty straightforward. You just need some ordered collection of events and pull out the minimum event at each step and process it, and you get the correct order, and the final result for your simulation will be correct. Once you move into a parallel domain, though, you have to figure out how to synchronize across the many processors in your job so you don't violate this timestamp order. In general, there are two schools of thought here, the conservative or optimistic approach to synchronization. Conservative is just where you do not allow any causality violations whatsoever. Optimistic is allowing for causality violations by executing events speculatively, and then if later you detect that there was a causality violation, you just have to figure out how to roll back from that causality violation. So obviously for this talk, since I already mentioned I'll be talking about speculative loads, we'll be focusing primarily on the optimistic synchronization scheme. And along with the optimistic synchronization scheme comes one last thing that'll be important for this talk, which is the computation of the global virtual time. So periodically throughout the execution of your application, you have to compute what's called the GVT. This is just the minimum timestamp of any pending events that have yet to be executed across the entire system. And what this gets you is, once you have this minimum timestamp, you know that everything that occurred before that timestamp that was previously executed speculatively can now be committed and finalized. So just to give a brief pictorial example here, we have the LP represented by that green marker. In the middle of a simulation, it has some prior events with time step 1 and 3 that it's already processed, and then some pending future events with timestamps 6, 7, and 9. So your LP will process events in timestamp order, and then at some point, for example, if we're running this in a distributed environment, say we get an event now with virtual time 4 that was sent from some other processor that we didn't know about previously. We have this causality violation, so we can't continue forward until we roll back the LP to a point at which it can safely continue forward execution. We can then insert this event that caused the causality violation back into our queue of pending events, and then continue forward execution normally. And then, of course, at some point, we'll want to compute a GVT. So let's say for this particular example, the GVT was computed to be 3, which again requires some global synchronization. Then at that point, we know that those first two events, 1 and 3, are actually meaningful work that contribute to the final result of the simulation, so we can commit them and free their memory. So when talking about the performance of PHOLD simulation, there are a couple metrics that I'll be using in this talk. The first is the event rate. This is basically your end-all, be-all of performance. It's just the number of committed events over the time taken to execute the simulation. So the higher the event rate, the better performance. That's our ultimate goal, is just getting the highest event rate possible. So some other metrics that actually contribute to the event rate. The first one, event efficiency. This is the number of committed events over the total number of events executed. And all this means is that, let's say you have 100% efficiency. That means every single event was a committed event. So every single event that you executed was useful, meaningful work that contributes to the final result. Anything less than 100% efficiency means there are some events that you executed speculatively, but it turns out they weren't the correct events at the time. So you had to undo that work, and that work was essentially wasted time. And then finally, of course, we have load balance. So what exactly does load balance mean in PHOLD? Well, that's what I want to go over a little bit in more detail. So first, what is load? What exactly are we trying to balance? So in the Charm++ case, Charm++ automatically measures the CPU time of all of the executing objects, basically just seeing how long every object takes executing its various entry methods. And this makes perfect sense in a lot of cases where all of our work is useful work. It all contributes to the final result. So in some, like science and engineering applications, every computation you do is meaningful. You're going to have to do it at some point. So balancing based on the CPU load ends up with balancing basically the work across PE, the various PEs. So this does rely on the principle of persistence, basically the idea that what you've done in your recent past is a good indicator of what you'll be doing in the near future. And again, this primary goal here is to just balance the work across all the PEs so that every PE has work to do, no PE is starved, and no PE is overloaded. However, does this make sense when we move to a speculative setting? So I'll give a small motivating example here. Let's say we have 3 LPs running in an optimistic simulation, and we want to look at sort of what they're doing and how that might affect the load balance. So let's say, to start off, every LP that we're looking at, each of these 3 LPs, have executed 5 events. So it's a reasonably safe assumption for at least a common case of simulations that executing an event is the time it takes to execute an event is uniform across events and across LPs. So from this, we would expect all 3 of these LPs to have roughly the same amount of CPU time spent so far. However, now if we look at committed events, let's say LP1 has committed 4 of its 5 events. Therefore, we know that LP1, the majority of the work it's done, has been useful work that's contributing to the final result of our simulation. Whereas the other 2, if they've committed 0 events, we don't know yet if their work has been useful or not. And finally, we can look at the number of events that are rolled back due to causality violations. In this case, we see that maybe LP2 has rolled back 4 out of its 5 events. So here we have a case where the majority of the work that LP2 has done has actually been completely meaningless and has not forwarded the simulation in any way and will not be part of our final results. So we have 1 LP that's done, majority of its work has been useful. 1 LP, the majority of its work has been completely useless. And then LP3 here, we don't actually know. It's done 5 events. We don't know yet whether those events will be committed or rolled back. So the important thing here, again, is that when you look at the CPU time spent by these 3 LPs, you're probably going to end up with roughly the same CPU time spent executing events because they've all executed 5 events. There'll be a little bit of noise, of course, here and there for the amount of time spent to commit and roll back events. But for the most part, the majority of the time an LP spends is on executing events. So how does a load balancer differentiate between these 3 LPs, and should it differentiate between these 3 LPs? The other question that we want to look at before we go into the specifics of the term load balancing framework and how it affects the performance here is how does the GVT affect balance? So right now in our current simulator, the GVT is a global synchronization, so it requires that all LPs cease execution while we compute the global minimum time, and then only once we compute the GVT can everyone continue. And we have 2 ways right now of deciding when to compute the GVT, and we see that these 2 strategies for triggering a GVT actually can have a pretty significant effect on load balance as well. So we need to take these types of things into account when doing load balancing. So the first kind of GVT is a count-based GVT. All this means is that we'll be computing a GVT every X events. And so the idea here is that, again, if we take the assumption that executing X events takes roughly the same amount of time, regardless of which events you're choosing, this should lead to good balance across the Ps in terms of the amount of CPU work done by each processor. However, it doesn't attempt to bound the optimism, and what I mean by this is it doesn't prevent LPs or Ps from getting very far ahead in virtual time. And what happens when these objects are allowed to go arbitrarily far forward in time is that at some point, someone's going to want to send him a new event that's probably now in his past, and that's going to cause rollbacks, lead to poor efficiency, and again, can negatively affect performance. So the count-based GVT attempts to balance the CPU load, but may lead to poor efficiency, whereas the leash-based GVT takes the approach of computing the GVT every X units of virtual time. And so the goal here is to keep virtual times roughly balanced across PEs. It keeps LPs progressing through virtual time at a roughly consistent rate. However, this strategy can lead to poor CPU balance across PEs. If you have one PE that has a very dense set of events within, say, 4 units of virtual time, and it has to execute 100 events, whereas another PE only has 2 or 3 events in that same window of virtual time, you're going to have a large amount of imbalance there. So for evaluating the performance of the different balancing strategies we're going to take a look at, and also the two different GBTs. I'll be using two benchmarks in this presentation. The first, PHOLD, is just a common PDES micro benchmark. Basically, whenever an LP executes an event, it creates a new event that it sends then to a LP chosen at random from the rest of the LPs in the system. And so we can change the event distribution, or how it chooses this random LP, to cause varying amounts of imbalance. And then we also have a traffic model, which simulates cars moving through a grid of intersections. The events are cars arriving, leaving, or changing lanes at these intersections. And each car has its own source and destination, and it travels from source to destination. Once all the cars arrive at the destination, the simulation is complete. And so again, we can change the distribution of cars at certain sources or going to certain destinations to achieve different amounts of load imbalance. So the first thing we look at is how does the GBT rate, or how does the GBT trigger affect the event rates and also the load balance. So we see here that if we look at both different models, the event rate being on the y-axis, again, higher being better, we see that the leash version of the GBT performs better in both cases by somewhat significant margins. And if we look at y on this next plot, where we're plotting the event efficiency, we see that because we're bounding the optimism and not allowing LPs to get too far ahead arbitrarily in virtual time, we end up with less rollbacks, and so higher efficiency means less overall work done to achieve our end result. And so the performance difference here is primarily due to efficiency, despite the fact that when we do the count-based GBT, we have roughly the same amount of CPU work per PE. So now with that insight, we can kind of come up with our overall load balancing goal, or what we want to achieve. So we still want to make sure, first and foremost, that all PEs do have useful work. We do want to balance the CPU load. However, the important thing here is that we only want to pay attention to useful work. When thinking about the count-based GBT, every PE is doing the same amount of event executions per GBT iteration. However, when a lot of that ends up being not useful work because we have poor efficiency, that ultimately results in lower performance. So we have to balance this goal of balancing CPU work with also maintaining high event efficiency. Higher event efficiency we can achieve by basically balancing the rate of progress of our LPs through virtual time. And again, this also leads to less overall work. So we have sort of two competing goals here for how we want to balance, and we need to make sure that we maintain both of these in some sense. Because at the other extreme, where we've seen high event efficiency can obviously lead to much better performance. At the other extreme, if you want 100% efficiency, you can just put all of your LPs on a single processor, get 100 efficiency, and then obviously have terrible load balance. So now with these goals in mind, we want to redefine exactly what load means for a parallel discrete event simulation. So like I mentioned previously, the default in Charm++ is to automatically measure the CPU time of each object, and that is directly attributed as that object's weight. Here we wanted to find different metrics for how to weight an object using actual characteristics of the PDES simulation. And we've broken these up into two categories, past-looking metrics and future-looking metrics. So past-looking metrics, again, are going to rely still on the principle of persistence, hoping that the work that we've done in the recent past somehow indicates the work we're going to be doing in the near future, with the extra caveat here that in cases where you don't have speculative execution, again, you know that whatever work an object has is, you know that everything it does is going to be meaningful and going to contribute to its situation, and therefore when you move it around from one PE to the other, you know it's still going to be doing the same exact work wherever it resides. Whereas now when you move into speculative execution, moving objects around also may change what work they end up doing because of the other LPs that are also co-located on a PE with it. So you have to be careful about using principle of persistence in that sense because the migration actually perturbs what each LP is doing. So for the past-looking metrics we've explored so far, or we're going to be exploring this talk, CPU time, we still want to see how effective the baseline metric is for load balancing. We also use a couple of timestamps to potentially balance the load. The current timestamp is just the virtual timestamp of the most recently executed event, with the idea being the further we are in virtual time, well, there's two things. We have less work to do before we reach the end of the simulation. So we're lighter in that sense. And also, the further we are in virtual time, the more likely we are to be rolled back because other LPs that are behind us may send us events. So the further you are, the lighter you are, and the earlier you are in the simulation, the heavier you are. A similar idea applies to the committed timestamp, which is just the timestamp of our most recent committed event. Same type of idea as the current timestamp, except now we're trying to only look at the timestamp of work that we know is definitely useful. And then the last two are, again, pertain to this idea of wanting to somehow capture a notion of what useful work is. So here we're just looking at the number of events we've committed, which is actually, this one actually is a common metric in some other related work in the field. But then the other one, potential committed events, this is just a slight modification of that, where we not only look at our committed events, but also the events that we've already processed that therefore may potentially be committed in the future as well. And then we have our future-looking metrics, which don't rely as much on the principle of persistence and hope to just predict the future based on what we already have at our disposal, knowing what we'll be executing in the future. So these are the next timestamp. This is just the timestamp of our next event, again with the same motivation that the sooner it is, the more likely it is to actually be meaningful work. The number of pending events we have, that's fairly straightforward. The more events we have to execute in the future, the more work we're going to be doing. We've also modified that slightly to be weighted by the timestamp of these events, giving more priority to events that are earlier and therefore more likely to be meaningful. And the last one is active events, which takes into account both the number of pending events we have as well as the number of events we've processed but not yet committed, because those may also contribute to our future work, because if we roll back, we may have to re-execute some of those events. So here we've got some benchmarks, or some runs of these different metrics under the PHOLD benchmark, where there's an imbalance in the amount of events that each LP has to process. Again, the left axis there is event rate, so higher being better. And we see that, first of all, the dark blue on the far left, that's with no load balancing. So we see that the vast majority of these load balancing metrics provide pretty significant speedups, up to 4.5x faster for the best count-based metric, and up to 2.5x faster for the best leash-based metric. And the next thing we see is that the dark red, the CPU time, does provide pretty good benefit, but we do have a number of other metrics that work even better. So for PHOLD, the ones that work well are committed events and the pending events. So in this case, the committed events and the pending events are both the modified versions where we take into account potential committed events, and we also weight our pending events. And the other thing to notice here is that for these particular benchmarks, the timestamps generally don't do so well, especially for the leash-based, and that's because in PHOLD, since there's all-to-all communication, and the leash is already sort of restricting how far ahead LPs can get, there's a very tight bound on what the timestamp of any of these LPs is going to be. And then to figure out where exactly the improvement here is coming from, we look at the next plot, which is efficiency. And we notice if we look at the two plots, for the shape of the count cluster there, the event rate here is actually quite similar to the shape of the efficiency. And that's because, again, the count, it already has a balanced CPU load. So here, the primary increase in the event rate comes from this increase in efficiency. So we still have a balanced load across PEs just by nature of how we decide to synchronize the GVT. But now we've got a better distribution of virtual time across the PEs, so we get higher efficiency, and that leads to our higher event rates. Whereas for the leash, we already had, if we look at the efficiency, we already had that high efficiency because we were restricting the timestamps. So here, the balance comes from the fact that now, by redistributing the PEs based on these different metrics, we have more even amounts of work to do in each leash window, so we end up with a better CPU balance. Moving on to the traffic, we see similar performance here, where we see up to 3x speed up in both the count and leash versions. Again, all the metrics improve over the no load balancing case, and we have a number of metrics that are also better than just the default CPU time. Here, the timestamps are actually much more useful because in traffic, since in this particular case, we're simulating what, for example, traffic might look like after a sporting event where a large number of cars are coming from a relatively small area and then traffic disperses from there. So because of that, because the imbalance is fairly localized, we have a wider distribution of timestamps across the PEs. So the timestamp balancing is actually the most effective in this case. And again, we see similar things with the efficiency. Here it's even more exaggerated in the traffic. The efficiency was basically 99% in the leash case. And again, it's primarily coming from the better balance in CPU load in the leash case and the better balance in efficiency from the count-based case. So what's next? So a lot of this stuff is still fairly early on. A lot of these results actually came from over the weekend. So we want to continue moving forward with this work, especially in a couple key areas. First, we want better visualization and analysis tools. So one thing that's tricky is with traditional tracing, it's hard to actually figure out what the load balance looks like. For example, you can imagine, like under the count-based GVT, if you just do a trace of CPU utilization, you're going to see very high CPU utilization across the board because everyone's always doing work. You just don't know if that work's actually useful or not. So some sort of notion of how to trace exactly what the work being done is, how useful it is, what the balance of that looks like. And we've started doing some of this. We have application-specific tracing that we've added to projections that allows us to trace, for example, the number of committed events over time. We also want a more diverse set of models. As we already saw just from these two models, different metrics behave differently across different models, so it's unclear as to which metrics will universally work best. We also want to see, this all so far has been for optimistic synchronization, but some of this can probably apply to conservative synchronization as well. Even though there we don't have speculative execution, can this model-based load balancing or metrics still do better than the CPU in cases where all the work is still meaningful? Another thing that will be touched on a little later today is vector load balancing strategies. So we have all of these different metrics that seem meaningful and somehow indicative of how the simulation is going to perform. But so far, when we've balanced, we've only focused on one metric at a time when we're doing the balancing. Whereas with vector load balancing strategies, we can look at the array of metrics at our disposal and balance not just for one particular metric, but for the entire array of metrics. And it kind of also goes back to the fact that when we're looking, we have these two competing notions of balance. We have our event efficiency balance and our CPU balance, and we want to find a balance, like that sweet spot between the two where we have still good CPU balance and good efficiency. And again, that's something that would point to vector load balancing strategies there. Also, some adaptivity within the runtime system or within the load balancing framework would help. We just saw the talk by Kavita where she mentioned the meta balancer is obviously able to choose for you the period and the strategy you use. Something similar here, we're looking at the characteristics of the different models, figuring out which metric is going to be the best representation of load for that model and adaptively deciding that rather than relying on the model writer themselves to figure that out. And finally, combining this with the GVT work, that's sort of the foundation of my thesis, is improving both the GVT and the load balancing. So some hints of that have already been shown here, where we see the two different kinds of GVTs and how the balancing affects each one differently. One thing I've also been working on is fully asynchronous GVTs, and the problem there, we end up in a regime similar to the count-based metric, where we no longer have this leash that's keeping things at a high efficiency. However, with the load balancing, we've seen that the load balancing can improve efficiency of a model. So if we can combine that with asynchronous GVTs, we can maintain that high efficiency, the good CPU balance, while also cutting down on synchronization costs. So that's my talk.
Questions for Eric?
This is a question I should have asked you in my office, but what about CPU time? You had CPU time, and you have committed events. That I assume is count of committed events.
Count.
But you could count committed time. That is to say, count only the forward time and only count it once.
Yeah, so that's
that is, if you roll back and come forward again, you don't count the second time coming forward.
Yeah, so that's another sort of one of the future things I want to look at is, so far I've kind of studied all of these different metrics in isolation, but combining things like CPU time and committed events. Another one is using the amount of committed events that I have in the past to predict, based on how many events I have in my pending queue, how many of those will be committed. So there's a lot of potential data to sift through here and a lot of different metrics to explore and combinations of different metrics. So that's a lot where the better visualization and analysis tools I think is going to be really important moving forward, because it's hard to get a grasp on exactly what these metrics are changing and exactly how they're affecting the load balance. And I think once I have a better idea there, it'll kind of guide how I improve the metrics moving forward.
Any other questions? All right, if not, let's go ahead and thank our speaker again.